Hello everyone, I am Dr. Siddheshwar Chopra and we'll be learning today the derivation for E equal to mc square, or which is popularly called as the mass energy equivalence, using the concept of relativistic mechanics. So let us start. Let us consider a particle which has been provided a force F and it moves to a displacement dx. So energy is defined as the work done in moving a body from one place to another. Infinitesimal energy due to displacement dx is given as dE equal to f dx. Now the total energy will be dE integration, which is E is equal to integral f dx, and the kinetic energy K now is the energy used to move a body from a velocity 0 to V. That is very important. So kinetic energy is equal to integration of f dx from 0 to V. Now the F force can be written in terms of dp by dt, where p is the linear momentum, and P again can be opened up as mv. So we have d by dt of mv dx in the bracket, which is also equal to, because these limits can be interchanged now, these so we have d of mv dx by dt. Now it is very important to understand here that mass is no more constant. Okay, so now the mass changes with velocity, and that is what we have learned already, what is called the relativistic mass. So mass is also variable here. So d of mv can be again opened up, m dv plus v dm. Now dx by dt is nothing but the velocity. So we multiply the velocity inside the bracket and we get integration 0 to v mv dv plus v square dm. Let me denote it by equation number 1. Now the factor mv/dv we can easily derive from what is the formula for relativistic mass. So from relativistic mass formula, which is m naught by root of 1 minus v square by c square, let us differentiate with respect to the velocity, and we have dm is equal to m naught times minus 1 by 2 into 1 minus v square by c square to the power minus 3 by 2 into minus 2v by c square dv. Cancelling out the common things and rearranging, we get m naught v dv by c square into 1 minus v square by c square to the power 3 by 2, which also can be written in terms of, again using the relativistic mass formula from the equation number 2, I convert m naught to m. So I can write it as mv dv by c square 1 minus v square by c square. Taking c square inside, we get mv dv by c square minus v square, and hence we have our important term here, mv dv is c square minus v square times dm. Now using the equation number 3, substituting for mv dv into equation number 1, I get integral 0 to v c square minus v square dm plus v square dm. Cancelling out v square, I get m minus m naught times c square. How does the m minus m naught come? Because you have to remember the previous units were from 0 to v, that was in terms of the velocity. But as you see here, you have dm, which is the variable factor. So the mass changes from the rest mass to the relativistic mass, or in fact that is the kinetic energy required to move the rest mass to the relativistic mass. So that is how you change the limits from m naught to m, and you get on the right hand side m minus m naught times c square. Now this formula is the formula for relativistic kinetic energy, and if you see carefully in this formula, if you take the term m naught c square to the left hand side, you have kinetic energy plus rest energy. So please read the paragraph here. The quantity mc square is known as the total energy of the particle, and the quantity m naught c square is known as the rest energy of the particle. That is the energy of the particle at rest. If the total energy of the particle is denoted by E, then we are left with E equal to mc square on the right hand side, and left hand side you have K plus m naught c square. And it is very interesting to note that the relativistic kinetic energy formula shrinks down to the classical expression of kinetic energy as obtained from Newton's law, and it becomes half m naught v square. In the same formula of the relativistic kinetic energy, you can substitute for m equal to m naught by root of 1 minus v square by c square, and using the binomial expansion, you can get to the classical formula. So this is all about mass energy equivalence. There is a very interesting another topic which is called massless particles. Now, what is a massless particle? It is the one which has rest mass of 0, which is m naught equal to 0. In Newtonian mechanics, particles can have energy and momentum if they have rest mass not equal to 0. Okay, but it is not the case in relativistic mechanics. You will see shortly why we are saying so. The total energy of a particle is given as E equal to mc square, and which is nothing but m naught times c square by root of 1 minus v square by c square. Using the relativistic mass formula, I square both the sides, I get E square equal to m naught square c4 by 1 minus v square by c square. Now we know that momentum of a particle is given as P is equal to mv, or in the relativistic mass terms, you can write m naught v by root of 1 minus v square by c square. I substitute for velocity from this formula P equal to mv, velocity is P by m. I substitute back for v equal to P by m in equation number 1. So we get E square is equal to m naught square c4 by 1 minus P by m whole square by c square. I rearrange this equation and finally I get E square minus brackets E square times P square by m square c square, and which becomes E square minus E square times P square c square by m square c4. What I have done here is I have multiplied and divided by c square in this second term. Okay, that is done because I want to convert mc square in terms of E square or E. So I have E square minus E square times P square C square by MC square to the power 2. So which is, if I open up the brackets, I get E square minus P square C square equal to m naught square C4. Here I rearrange it and I get the final relation between the energy and momentum. This is the relativistic relation between energy and momentum, which is E square equal to P square C square plus m naught square C4. If you see carefully here, what are the massless particles, which are as given in the definition in the beginning? M naught is equal to 0. So according to Newtonian mechanics, if m naught was 0, then the energy also will be 0 for the particle. So that is what was the massless particle. But if you see here carefully, now if you put m naught equal to 0 here, you have E is equal to Pc. So for a massless particle, example is photon, E is equal to Pc. So that was all for today's lecture. Thank you everyone for the patient listening.